This is the brief on mathematical symmetry and its physical application in tensors. So we're basically looking at these really powerful math tools that let us understand physical change. You know, how a complex object, a tensor, can take forces like stress or fluid flow and just break them down into simple, measurable parts. First up, let's talk about the generalized Kronecker delta. It sounds like a mouthful, I know, but it's really all about a deep, fundamental symmetry. The key insight is that this complicated-looking thing can actually be built from a product of much simpler functions. And what's really cool is that this definition holds true no matter which way you orient the equation. So why does that structural elegance matter? Well, it's because it's the key to a core application in physics. It lets us take any general physical force described by a tensor and cleanly split it into just two components. Second, you've got the symmetric component. This part is only responsible for deformation, stretching, compressing, or shearing an object. Think of it like squishing a sphere into an oval. And finally, there's the antisymmetric component. This piece of the puzzle handles only pure rotation. It changes an object's orientation in space, but it doesn't alter its size or its shape one bit. Understanding this unique breakdown into symmetric deformation and antisymmetric rotation is what lets physicists analyze phenomena like stress and fluid dynamics with such precision.